Hello, I'm David. I'm the coordinator of the Maths Learning Centre, and it's summer 2023, and this is a revision seminar for Maths 1B. Cool, that's enough of my face for now. All right, well, I've had several requests. Oh, damn it. I've had several requests, and I'm going to do my best to do several of them. And they will be in no particular order, because that's how they came. So the first thing is a limits thing. I'm going to say, it looks like, oh crap ass. It looks like I'm going to talk, all about limits at infinity and tell you everything you want to know. I might, but really I'm just going to do this example. And that will give us enough to talk about. All right, I'm going to read it out. The limit as n goes to infinity of a fraction which has on the top the square root of n to the power 4 plus 28n squared, all of that's under the square root, plus kn squared, all over n plus 48 plus 3n squared is equal to 19. What is k? Cool. So when I first saw this question, I didn't know this bit here was here. And I read it and I went, okay, what's going to happen here is that this fraction here has the unknown n in it, and then it says that n goes to infinity. So by the time I've calculated what this limit is, there won't be an n in it anymore. It'll be gone to be replaced by, well, infinity, and then we can't do that, but we'll do some careful manipulations so that there won't be the number n or the letter or the symbol infinity anymore. And that would expect, to me, I would expect there to be a k as part of that formula somewhere once I've got to the end. And so there'll be some formula involving k equal to 19, and presumably I can solve that to figure out what k has to be. And then I looked at the question and went, oh, what is k? Cool, great. But the question could have been something else, I don't know, but I didn't even notice that equals 19 until I wrote this bit down. And then what I would have done is just found this limit, and hopefully there'd be a k left behind. I don't know what the point of that story is, but it's just that that's how I think about these things, is to try and make sense of what's there before you look at what the question is asking you to do. Because if you just went straight to the bit where it asks you a question, what is k, you're going, what k? And you'd have to go back and find it. So it's best to have a good look at what's there before you look at the question. All right, cool. So the things I know about limits at infinity is that when n is an extremely large number, like 1,000,000, then n squared will be 1,000,000,000,000. No, you're saying? No, that's right. 1,000 million is a billion, and 1,000 billion is a trillion. So n squared will be like 1,000,000,000, and n to the 4 would be whatever that one is. But this one will have, if n's like 1,000,000, this one will have 12 zeros, and this one will have 16 zeros. And so, no, crap, 24 zeros, but lots of zeros on the end when you write it. So this number, n to the power of 4, is way, way, way bigger than this number, n squared. So if n is extremely large, this is much, much bigger than this, and so this isn't going to make all that much difference to the size of this number. And so I could imagine that if n is really huge, that's just the square root of n to the power of 4, approximately, which means it's approximately n squared. And so the whole top of this fraction is, approximately n squared and k times n squared. So it's, the size of it is n squared-ish. And the bottom, the size of that is n squared as well. Because when n is like 1,000,000, n squared's way, way bigger than either of these things. And so they're not going to make much of a difference. So it looks like the top's roughly n squared sized. the bottom's n squared size, so those n squares are going to cancel each other out and we'll just get a plain number. So that's good. It's doing what I expect it to do. I expect this answer to be a number and not involve any n's. It's just without the limit, right? So the n squareds I'm expecting to approximately cancel. All right. But that's some great reasoning, and if I was not being asked to show my working, I would just run with it, right? I go, well, this is approximately k plus 1 lots of n squared over 3 lots of n squared, so it's k plus 1 over 3 equals 19, and so k plus 1 would be 3 times 19, and so k would be 3 times 19 minus 1. That's a heuristic. That's the official word for a problem-solving strategy, and a reasoning that's not necessarily straight-up mathematical algebra, but yeah. So I'm expecting the answer to be k being whatever 3 times 19 minus 1 is. That's what I expect. But I'm not sure. So I'm just going to do something. So the idea of when you go to infinity, and that idea of one number being much bigger than another, is all wrapped up in this one thing we know about limits at infinity, is that the only limit that we know for sure is that the limit as n goes to infinity of 1 over n is 0. This we know to be the truth. And it's pretty much the only limit at infinity that we're absolutely certain of. Like that actually comes out to a number as opposed to just doesn't exist. And so if I can write everything in terms of 1 over something on the bottom that goes to infinity, it doesn't even matter what this is, as long as this thing goes to infinity, it'll come to 0. So you could have the limit as n goes to infinity over thing that goes to infinity is 0. This we know to be true. This is not this is a thing that I'm thinking. It's not good maths writing, but there we go. It's good maths thinking, not good maths writing. So if we can rewrite it in terms of that, that'd be great. And the great thing about fractions is that you can divide the top and the bottom by whatever you want, as long as it's not 0, and it doesn't change what the fraction's equal to. So for example, if I divided the bottom of this by n squared, I'd have 1 over n and 48 on n squared and 3, and I know that 1 over n goes to 0 and 48 on n squared goes to 0. Actually, it could just be like a plain number on the top. That'll work just as well. It doesn't matter whether it's a 1, it could be a 48 or a 216 or a minus 50. Excuse me. Okay. On the top, I know that this is approximately some multiple of n squared, so if I divide it by n squared, it should come to a plain number. So that's what I'm going to do. If I divide this by n squared, I'm going to get a k. If I divide all of this by n squared, but this is all joined together by the fact that it's under this root sign. I can't divide each of these things separately by n squared because it's trapped under that root. So now I'm going to actually do the working. So all of this thinking in an exam would have happened in about 20 seconds. Okay, I'm speaking it all out and reasoning it through, but when you look at it, it would have all happened very quickly. So don't think that it takes 20 minutes to actually do this. Oh, well, what, 10 minutes to do this. I just wanted to say it all aloud so that you could see what was happening and hear what was happening. So, just to go back a bit, that thing where you say if this is really huge, just the biggest part of it is the bit that's there, but treat the root separately so that you can deal with the square root and then look at that bit. That idea where you look at the really big bit and you say it's as big as the biggest part, the mathematical working that goes with that is dividing by the biggest thing that you see on the top and the bottom. That's the working that goes with that reasoning. So I would go, all right. I'm just going to deal with it equals 19 later. And so I'm going to divide the top and bottom of that fraction by n squared, because the top is approximately n squared because it's square root of n4, and the bottom's approximately n squared as well. I get that. Yep.
Is the division of n squared inside the brick or outside?
Outside. Okay. So the thing about roots is that they expand out over division. So if this bottom was a root as well, then I could just do the division inside the root. And so that's what I'm going to do. I'm going to arrange for the bottom to be a root as well, and that's going to be... So this is the full working. You can normally skip this step. So this n squared I've written as the square root of n to the power of 4. And then that root can come out across that division, because that's how roots interact with division. And then that means that both of these things get divided by n to the power of 4. And that move can be done in one step. You can go, oh, well, dividing by n squared outside the root is the same as dividing by n to the power of 4 inside the root. Same as dividing by 3 outside the root is the same as dividing by 9 inside the root. So n to the 4 divided by n to the 4 is 1. 28n squared divided by n to the 4 is 28 on n squared plus k. And so now, each of the pieces of this limit I can do. That's just a number, it'll stay the way it is. 28 on n squared, well, n squared goes to infinity and I divided by it, and so that becomes 0. K doesn't have an n, so it stays as a k. That becomes 0. That becomes 0, and that becomes, well, stays as a 3 because it doesn't have an n in it. And so this becomes, just to be absolutely clear what happened, that all of these different pieces became zeros when we did the limit. And so I get that k on 3, and I know that that's equal to 19, right, sorry, 1 plus k on 3. Good. It's not a times 0, David. 1 plus 0 is 1, not 0. And so I get 1 plus k is whatever 3 times 19 is. Well, 3 times 20 would be 60, so that must be 57. And so we get k is 56. Yep.
Can you use a non-L rule because it's an infinity over infinity?
So I'm going to repeat that for the purposes of the video. And the question was, just to make sure, can you use L'Hopital's rule when you've got an infinity over infinity? And so you're looking at this and you're saying, well, the top's obviously infinity because you've got an n squared. Bottom's obvious infinity as well. That's infinity over infinity. Could I have used L'Hopital's rule? Yes, you could.
Because I tried to do it, but what happened was it just expanded that into more product rule.
Yeah.
And
And it just got worse and worse? Yeah. So that root, if that root wasn't there, L'Hopital's rule would be great.
Right.
It'd be awesome because this is a polynomial and just keep differentiating until all the n squareds disappear. But the root just turns it into just horrible, right? Because that power of a half there, it's just... So L'Hopital's rule totally works, but the root just makes each derivative harder and harder to do. And so this is actually not that difficult compared to that. It's not easy, but it's easier compared to that. But L'Hopital's rule would have worked. Like in a technical sense, L'Hopital's rule only works if n is allowed to be the numbers between the whole numbers, but it doesn't matter. Like, yeah, because n's technically usually only allowed to be a whole number, but whatever, it's fine. But this is quicker because you don't actually have to show all of this working. You could probably have put in like just a note to say divide numerator and denominator by n squared, and then skipped straight to this line. That would have been okay, as long as you put a note to say what you did, because a person reading that would have gone, a lot just happened there. I mean, the person who was marking an exam would have totally known, right, because that's exactly what they would have expected to do. But you, if you're doing something while you're studying, you should always put a note to say what you did, because future you needs to know. Yeah. How do people feel about that? Cool. All right. Was there something in there that is useful beyond this specific problem that you would like to reuse in the future? A move that I made that you think, yes, I want to try and remember that move so I can make it in the future. Divide by the highest power? Cool. This moving the root. Yep. So, and that's totally straight up algebra move that your lecturers assume you remember from when you learned roots and powers in year 10. But you won't. Yeah. Can I just adjust that divide by the highest power thing is? Just note that if a power is under a root, the highest power is like half of what it says. Yeah. And if this had been a cubed root, that would have been even smaller. Cool. All right. While we're at it, any other thoughts or questions about limits that you want to talk about? Yep.
There was a question on Mobius that was limit 8 to the t minus 2 to the t. Do we have to memorize that as 8 to the t would have derivative because we use logarithms? I don't know how to say it. The rule that I said.
Mm-hmm.
We would use it because it's like a 0 over 0 or infinity over infinity. But because it's 8 to the power of t, we don't actually know like how to find the derivative. And there is a easy way to just say it's ln whatever that number is multiplied by that number to the power. But do we have to just memorize that, or do we need to show working why that is?
Yeah, are you talking about the derivative of the function 8 to the power of t?
Yes.
You're supposed to just know that. You don't have to explain why it is the way it is. So just a second, just as an aside. The derivative of that is 8 to the t, and then you have to multiply by ln 8. And you're allowed and supposed to just know that rule. And you're thinking, do you have to prove that rule? And you can if you want. You can prove it by going, well, that's equal to e to the ln 8 to the power of t. And then when you differentiate e to the power of, it's the same. Whoa. When you differentiate e to the power of, it's the same. But you have to multiply by the derivative of that, which is the number ln 8, because that's what's attached to the t. And so when you do the derivative, you get e to the ln 8t, because that's the times ln 8, and this was originally 8 to the t. Yeah. And that's how you get to there. But that's how to do it, because the number ln 8 is just a number. It's not a function anymore, it's the answer that a function gives. Any more than root 2 isn't a function, it's just a number, it's somewhere between 1 and 2. So you're allowed to and encouraged to just use this rule if you want to differentiate things.
So that's that equation where it says m is derivative as ln a times b to the.
Yeah, so the derivative of a to, can I just say, the derivative of a to the power of x is ln a times a to the power of x, is that what, yeah. Yep. Cool. And it works even for e because ln of e is 1. Technically we define the derivative of e, anyway, e to the power before that. Logs were defined before exponentials in the history of maths, actually, and which is just fabulous. I like logarithms. Okay. So a point I want to make is, that you've made for me very well, is that just because you're doing limits, it doesn't mean that they won't expect you to remember everything else you ever learned. So, and technically that derivative is somewhere in high school, or in Maths 1A at least once. And so, yeah, now you know. Cool. That's great. Particular solutions to DEs. Okay. It's specifically the DE's particular solutions things that you have in Maths 1B, which is constant coefficient homogeneous, no, not, oh crap house, not homogeneous. Second order constant coefficient differential equations. Oh, second order linear constant coefficient. Yes, sorry, one more adjective. All right. So, right. Find a particular solution to this differential equation. Y double dash plus 5y dash plus 6y is equal to sine of 3x. Okay, so let's just talk this through. This is a differential equation because the equation mentions a derivative. And it's a linear differential equation because the only way that the derivatives of y have been combined is by multiplying them by stuff and adding them together. And it's the constant coefficient linear differential equation because the things that the y and y dashes have been multiplied by are constants. And it's second order because there's a y double dash. Sweet, okay. But it's not homogeneous because this is not 0. You'd think homogeneous means the same, like means all the same. That's what homogeneous means in English, or Latin. And that is the sameness that they're referring to is that everything is about y and multiples of it, whereas this is not about y, it's only about x. That's why it's not homogeneous. Yeah? Yeah?
Isn't that how you usually come with a y equals something in the front of that? So
So you're saying like that usually comes with like a y of 0 equals 7 or something like that?
that and also like y of something equals
Yep. Okay, so it usually comes with the thing you're describing, like something like this, y of 0 equals 7 and a y dashed of 0 equals minus 5 or something like that. Is that what we're talking about?
No, as in like the function of y. It's like y of x equals something and you have to find the derivative of that y in that.
No. So what you're thinking of is when they tell you the solution and they ask you to verify that it really is a solution. And so, good point. If they say, is this a particular solution to this, and they give you an answer, then you differentiate it, sub it in, and see if it comes out to sine of 3x. But if they haven't told you what it is, you're going to have to find it yourself. That's a classic maths thing, is to ask you both kinds of questions. And to verify that this is a solution is usually much quicker and easier than any other thing that you could do. All right, so we're going to find a particular solution to this. And the way to find a particular solution is to follow the vibe of differential equation solving, which is to guess a kind of solution that it might have and then figure out the correct one of those. This is how solving differential equations goes. So if you do a differential equations course in the future, it will go like that. Every couple of weeks, you'll learn a new way of thinking, here's what I think the solution ought to look like, and here's how to find out which one of those it is. That is one of the big ideas in differential equations, which seems like trial and error, right? And it is. It's just sophisticated because you know a good thing to trial. Okay, so whatever the function y is, it's some function of x. I have to pick a function. I'm trying to guess a function of y that when I have y and its derivative and its second derivative, the thing that I get at the end has a sine of 3x. I know a function whose derivatives have sine of 3x in them, and it's sine of 3x. But I know another function whose derivatives have sine of 3x in it, and that's cos of 3x. And so what I'm going to do is I'm going to say maybe y is made of some combination of sine of 3x and cos of 3x, so that when I do the derivative and the second derivative and I combine them all together, somehow all the causes cancel out and I end up with sine of 3x. That's the thing that I'm thinking of. But that is the idea for all of them. Depending on what you have here, you try to guess something that has this in its derivatives. And everything that could have this in its derivatives, you have to include in y. Yeah. Or the other way around, have this thing and all of its derivatives. That'll work too. It works the other way around. So, but yeah, you need to think of things that have this as a derivative somewhere, as part of its derivative. So I'm going to, last thing to mention is this just a second. This article, that is the correct English grammar word for this kind of word, as opposed to the. Means it's just one of the possible ones. Not to say that there's, it's not that there's only one answer, it's just that you just want one of them. Anyone will do. It's like, pick a student, I just want one of them. Pick the student implies that there's only one student to pick. It's not find the partial solution, it's find a partial solution. In languages without articles, this is really difficult to describe. In languages like French, where they say the for everything, it's difficult to describe. And you have to use the word one. But in English, we have the word a, and that is what it means. Just wanted to point it out, because it happens in lots of other situations. I have students in Maths 1A who come to their first Mobius question with an a in it, and they think that there's only one answer, and actually there's lots of them, and the Mobius only wants one, and you can put whichever one you want. And it takes some getting used to if you've never had an a question in maths before. So just point it out. Okay, so I have to think of something that has this as an answer. Cool. Except there's some batteries not included, which is you also have to pick something that won't make this answer come out to 0. Because there are some things you can pick for y that will make the answer 0 and not sine of 3x. And you can't pick any of those things because they won't come out to sine of 3x, they'll come out to 0. So you actually have to first find what the solutions are to the homogeneous equation before you can pick your particular solution. Sadly. Damn it. So the homogeneous DE is this. And its characteristic equation is lambda squared plus 5 lambda plus 6. So you do the move of replacing the double derivative with a squared and the single derivative with a power of 1 and the no derivatives with no lambda. And it's called a characteristic equation because it's actually the eigenvalues of a matrix, which you may or may not learn in differential equations if you ever do another course on it. But yes, we are finding eigenvalues. That's why they use lambda. So, yay. Because derivatives do to functions what matrices do to vectors. So, yeah. Yay! One of the reasons to learn linear algebra is so that you can reuse some of its things in calculus. So, I see you making faces, but I'm sorry, it's the way it is. So I have to solve this equation, which means I either use the quadratic formula, or if I'm really, really lucky, I can think of two things that add to give 5 and multiply to give 6. 1 and 4, 2 and 3, yeah, that'll work. Okay, so, and so lambda is -2 and -3. And so with two different solutions, we would say two solutions are y is e to the minus 2x and e to the minus 3x. And neither of those are this, so I'm good. Yay! Anyone want to pause for a moment and think of what this equation would have had to be in order for one of these to be that?
Imaginary numbers.
Yeah, you'd need some imaginary numbers. That's what produces the sines and the causes.
Yeah.
You'd need the solution to be plus or minus 3i.
Yeah, right.
Yep.
Given we're finding a particular solution, you don't have to find homogeneous.
You have to find the homogeneous ones just in case these come up to be that answer. Because if they do, you can't use this as part of the particular solution. You've got to multiply by x. Yep.
I was under the impression that it was if the particular solution equals the homogeneous. Is it that as well, or is it just if that?
Well, it's not this bit. It's yes. If the particular solution you would pick was part of the homogeneous. Yeah, and we'll do one where it is. So that's not a problem. And say, so I would have picked this. So I would choose a particular solution, y equals something, oh crap, I can't call it s. Something times cos of 3x plus something times sine of 3x. And neither of these is listed here, and so it's okay, I can run with this. What was that? So if one of these things was listed here, I would have to multiply these by x. Sorry? Because the people who have trod this path before us discovered that it works. There are reasons. They're complicated. I can't remember what they are. If you do a differential equations course, they'll tell you, and you'll forget because they're complicated. So that's the reason. But it definitely won't work if you leave them as they are. If this had been an e to the minus 3x up here, I would not have been able to use it as a particular solution because it's a particular solution to the homogeneous one, not to this one. So it says it is a solution just to the wrong differential equation. And so then I am fairly confident that if I differentiate this and sub it into there, one of the options for A and B will work. One of them. Possibly more than one, but at least one. And so I would get, okay. So the A will still be there because it's multiplied on, cos will become a minus sign, and the 3 will come out because of the chain rule, and the B is still there because it's multiplied on, the sign will become a cos, and the 3 will come out because of the chain rule, and then y double dash will be minus 3a will still be there, the sign will become a cos, and the 3 will come out, so that'll be a 9 now, and the cos will become a minus sign this time. Okay, so there's my y dash, there's my y double dashed. What I actually need to do is put in my, now what I have to do is put this back into the original to find whichever of them is the right one that makes it comes out to sine of 3x. And so I need 5 of y dashed, which will make this a 15 if we multiply by 5. But I'm just going to put it over there with the signs if that's okay. So we've got minus 15a sine of 3x and 15b cos of 3x. And then 6y is 6a cos of 3x and 6b sine of 3x. Cool. And this is all supposed to add up to sine of 3x. So if I add these three together, it's supposed to be sine of 3x. If I have all of this together, it's supposed to be sine of 3x. So if I do the sum, I should get sine of 3x and this is going to be 15b minus 3a lots of cos of 3x, and minus 15a minus 3b of sine of 3x. Just adding them all up. Like those become this and those become this. Which is why I lined the coses and sines up when I wrote them down so that I could do that. So you may notice that I have done some things to try and avoid me making mistakes along the way. And one of them was not putting this all into one great big, like, not writing down y double dash plus 5y dash plus 6y equals and then subbing things in, but just writing them as separate lines that I could line up on top of each other. It just makes it a little easier to do what I want to do. And then I don't lose minus signs so much, and yeah. Okay, so the functions cos 3x and sine 3x. I'm just going to stop for a second. It's not cheating. Good. The functions cos 3x and sine 3x are linearly independent. They are in fact a basis for this subspace. Anyway, any functions that you can make out of cos x and sine x can only be made in one way. And so this function is made of sine x and cos x, and this function is made of sine x and cos x, so I can equate the coefficients of cos and sine. And it's just a feature of how cos and sine behave. And so that means that since there are no cos x's here, this must be 0. So I must have that 15b minus 3a is 0, and minus 15a minus 3b must be 1. And that's two equations and two unknowns, which is enough information to figure out what a and b have to be. Actually, I'm really lucky. A is equal to 5b, and if a is equal to 5b, I've got 15 times 5b minus 3b is 1. Wow.
A is equal to minus 5 on 78.
Fabulous.
B is negative 1 on 78.
B is negative 1 on 78, and because A is 5 lots of B, A is minus 5 on 78. Cool, and so therefore my particular solution is minus 5 on 78 cos 3x minus 1 on 78 sine of 3x. Yep.
One question. For that specific question and other questions where we have to do some working, do we need to do the workings that are not in-house, I guess, the things that they are grading us? So for example, with that, you can just put in the calculator and find A and B. That's one safe.
If they haven't...
show the working out, or like for matrix, you can put it in the calculator.
If they haven't specified how to do it, then you can use your calculator. Personally, I feel safer if I write the working down, but that's just me. You might feel differently, and that's up to you knowing yourself what you are more or less likely to make mistakes in. Me, I will always transcribe things wrongly into my calculator, and so I don't like using them. Also, I just don't have one today. So I've got a whole computer, I guess. I could have done that, but yeah. And I just will say that don't always go to a calculator. Just have a look to see if the answer's already there. Like maybe it turned out that this just told you what A was, and it's like, well, there's no point in using a calculator now. Like if it just said minus 3A is 0, and therefore A is 0, like, yeah. Because some people go to a calculator without stopping to think, actually, can I just do it now? Would it be faster to just do it than to enter it into the calculator? But whatever. When you're stressed out, do whatever makes you feel the safest. So, yeah. You've got to take into account the exam stress when you make that decision. So, How do people feel about that? So I guess all I want to point out is that in the end I didn't end up using this, but I had to do it just in case. Just in case the thing that turned up here was already part of the thing I was hoping to use as the particular solution. So if the equation had been this, if it had been this, same left-hand part, but a different right-hand part, I would have thought, okay, e to the minus 3x, if I differentiate that, it'll just still be there with different numbers, and so that's a good guess for my particular solution, and so I would have tried some other number times e to the minus 3x, except e to the minus 3x is in the particular solution. Not particular, is in the homogeneous solution. Just a second. Homogeneous solution is a bad phrase. It's not the solution isn't homogeneous. The equation it's a solution for is homogeneous. So is a solution to the homogeneous equation. So instead try y equals x times e to the minus 3x. Yep. And if x e to the minus 3x was also part of the homogeneous solution, you would try x squared e to the minus 3x. You just keep putting extra x's until you run out of bits of the homogeneous equation solution.
What was that equation versus y equals y homogeneous plus y?
Yep. That is all the solutions, or the general solution to this original equation. So what we've done here is we've just found one possible solution, where is it, to this original equation. This is just one solution that makes this work, but there are in fact many. You would expect there to be many because derivatives, when you integrate them, you get constants. And so there will be more solutions, and the rest of the solutions will be this plus a times this plus b times this, or C1 on C2, or whatever you want to call them. Yeah, so this thing plus c times this plus d times this. Yeah. Yay! Because it's an affine subbase. So, yeah. So all I want to say is that the other kind of equations that you get, there's a list in your notes that says if you see this kind of remainder or whatever they call it, I don't think I even give this a name, they call it Rx, I think. If you see this result for a non-homogeneous constant coefficient second order linear equation, there's a table in your notes that says if you see this thing, then do this thing. I find that table actually quite difficult to read. So here's the thing. You should put the thing that's there with possibly an unknown coefficient and all of its derivatives. That's what you should put. So if you see, you know, something y dash plus something. If this is what you've got, numbers in these spots, and a thing here, then for the particular solution, you put y equals thing, but with an unknown coefficient, like the multiplier down the bottom, not at the top. And all of its derivatives. I'll show you what I mean by that. So if you saw equals sine of 3x, well, then you would go sine of 3x with a different number, and the derivative of sine of 3x is cos of 3x. There'd be a 3 there, but we'll put a different number there. And the derivative of this is sine again with a minus, but that's just a constant, and we've already covered that with this a. And so I've now covered all the derivatives of this. But if I had, we need to put a box around this so you can see it. If I had something like that, you know, it doesn't even have to, you could have any number there, it doesn't matter. I would have something x e to the 2x. And then the derivative of this would be keep the x and differentiate the e to the 2x. Oh, that's the same as what I've got, but with a different constant, so that doesn't count as different. And the other part of the derivative would be differentiate the x, 2x. Okay, cool. So I put that. So differentiate this, and any part of it that's already part of the original, just throw it away, and keep differentiating until you've got all the things that you could possibly have. And if I differentiate this, I just get e to the 2x's again. And so this is what I would put. Yeah. That's how I think about it, and it means that I have one rule instead of 6. And if I have one more. I'll try y equals, so I have something x to the 5 and something x. If I differentiate this, I'll get an x to the power of 4. If I differentiate that, I'll get an x to the power of 3. If I differentiate that, I'll get an x squared. If I differentiate that, I'll get an x, and I've already got an x, so that covers that. If I differentiate that, I'll get a 1. If I differentiate, so f times 1. If I differentiate that, I'll get a 0, which means I'm not adding any more stuff. And so I've now included all the derivatives of all of these things, and that is the thing I need to use. Just in case, like it's totally like a just in case.
That's explained the whole time.
Yeah.
Yeah, I only thought of this year. I always told people the rules, like if you see a polynomial, then do the highest power and every power below. And if you see a sign, then do that. And then if there's two of them multiplied together, then multiply them together. And I just went, oh crap, well, there's so many rules. And then suddenly this year I went, you just include all the derivatives. This one just here. Okay, so I'm just going to write down that if you do the derivative of x e to the 2x, you get 2x e to the 2x because the x stays and the e to the 2x differentiates. And you'll get 1 times e to the 2x. And the x e to the 2x is already covered. And so you put the e to the 2x. And now if you differentiate the e to the 2x, you just get e to the 2x again. So that's already covered by this. And so I'm now not going to get any new derivatives anymore. Yeah. Yeah.
So you always start with ax equals to x and differentiate that one. So whatever the original.
Yeah.
Just to clarify, your rules get whatever the term is,
Yep.
we have that multiplied by a constant that we don't know, and then we find all the derivatives as well.
And whatever constants are part of those derivatives, ignore them and replace them with new unknown constants. And any part of the derivatives that's already covered, then ignore them, and you don't need, you've already covered them. So, yeah. This just, I had this whole, and I went, oh my goodness, it's so much easier. I don't have to remember anything. Because it's a differential equation. Of course you're going to put derivatives in. So it just made me feel so much better. And of course, if you practice this enough, you won't have to do that move. You'll just remember what you would have done anyway. But it's like your times tables, right? Nobody remembers 7 times 8, but it's 56. But they might just remember 7 times 6 and be able to figure out the next one. And so that's the idea. Like I can do this, and for those times when I can't remember, yeah. I mean, you'd still put the list on your cheat sheet, right? But it would mean that just in case your brain just goes, right? But yeah, anyway, that's just me. How are you feeling? Because you asked the question, so, okay. All right. Okay. All right. I'm going to spend at most 10 minutes on big O notation. So tell me what is bothering you about big O notation.
I don't know. Well, there was one property about property 1.5, which just says we say that the function g of h equals big O h to the power of n for some n is an element of natural numbers, and then it just goes lim h equals h to 0 of the absolute value of g h over h to the n is less than infinity. And then I'm not too sure, because like it's come up in a couple of questions where I didn't know what to do, and I was literally go to use big O, and I'm like, it never really was explained on how to use it properly.
Yep. So I'm just going to repeat some of that. This is the property, which is more or less a definition in the notes. And then whenever they use it, they never use this definition. Right? And they just sort of like say stuff and go, I used big O. And go, did you? And that's sort of how you felt. Is that, I'm getting, yep, okay, cool. This is how it always feels. Computer science uses big O as well. And it's just as crap over there. And I tried for years to try and help them find better ways of talking about this. And they can't do it. And this is my major teaching problem that I'm trying to solve at the moment, which is how to help people teach people about big O. Because I don't understand all of it, because no one's ever taught me correctly. But what I will tell you is that the way people use big O is to not use the definition. But I will talk about it a little bit. 5 more minutes. I'm going to talk about it a bit. So big O as a notation is weird and different to the way we use other notations in maths. So the way we use the equal sign here is not how we use the equal sign in the rest of maths. Okay? You have to read this equals as the word is. Which you can read the word, the symbol equals as the word is, right? You know, x is 4, that's perfectly good read equals. But this is more using the word is in the sense of like, x is green, right? G of h is a function which has the description big O of h to the power of n, like it is in the category of big O, like as opposed to being equal to whatever weird-ass thing big O is. Right, so we're actually saying that we are allowed to describe the function g of h as big O of h to the power of n if this thing happens. And when they say less than infinity, they just mean is equal to a number. Right. Let's just think about this. G of h divided by h to the power of n is like how big g of h is compared to h to the power of n. And we're saying that how big g of h is compared to h to the power of n, as n gets really small, is a number. So that means it's like approximately a multiple of h to the power of n. And you've used this reasoning before when you made a guess at what this answer was. I went, n plus 48 plus 3n squared. When n is really huge, that's not all that different from just 3n squared. That's big O reasoning. Only when n is huge as opposed to when n is small. So in computer science, they use big O reasoning when n is a really big number. And in maths, they use big O reasoning when n is a really small number. So it's important to know that if you do computer science courses, it'll turn out either way. So if n is really huge, this is not that different from 3n squared. If n is really small, like really close to 0, this is not that different from the number 48. So from a big O point of view, big O for small numbers, this is in big O of a constant. big O for really big numbers, this is big O of n squared. That reasoning where you say, what's the thing that controls the size of this, that's what it's about. And when people talk about big O, they almost always talk about that sort of floppy reasoning. They're not precise about it. So you notice, well, they gave this definition, but at no point did they calculate a limit. Well, that's just because that's just the way they do it. And so the general rule is, so the general rule is that, you know, just as an example, 3n squared plus 5n plus, you know, something like that, is big O of n for n going to 0. It's just really important to talk about the small n's. So if n is a small number, like 1,000th, then n squared would be 1,000,000th. And so it's not going to make much of a difference to the size of this number because it's in millionths compared to thousandths. That's the idea behind it. So if I did divide this by n squared, just to be formal about it, the limit as h, oh crap, it's h, fuck. You see, you can say I really don't like big H. I don't swear very often. Not real swearing. Usually, if I'm in presence of mine, I'll usually say frel, but which is from the TV show Farscape. So if I divide that by h, I'll get 3h plus 5, the limit of that. Damn it. And that doesn't make any sense. No, that's okay, which is a constant, it does make sense, which is a constant which is less than infinity. Right. Which is a constant. We did it. And see, look, is equal to a number. Right, that's what this means. So if the limit comes out to be equal to a number, which it is, then this really is big O of h. But nobody ever does this working. They just go, oh, well, h squared is way smaller than h when h is small, and so and we don't care about the constant multiple, so it's just big O of h. And then there's these other general rule, that's general rule number 1. And then general rule number, so a polynomial, when h is small, is big O of its smallest power. And a big O of a higher power is way better because h to the 5 when h is 1,000th is quadrillions or something. And the other thing is that if you multiply big O of h by h, it becomes big O of h squared. So h times big O of h is big O of h squared. That sort of idea is a thing. And similar things. That's it. I don't want to say any more than that. But in Maths 1B, that's pretty much the deal. And if you do statistics and numerical methods or any other kind of numerical methods, that's pretty much the entire of the reasoning. You'll go, oh, look, the biggest power in this is h to the power of 4. Like the smallest power is h to the power of 4, it's big O of h to the power of 4. But yeah, all I want to say is just be careful if you do computer science because it's the other way because they're using big numbers and not small numbers, but it works okay to say, is my number h big or small? And whichever one it is, which of these powers is the biggest thing? And that's the big O. Yeah. So my instincts are that it's not going to really come up much other than just to ask you, what's big O of this?
That's what I was going to ask, if it's related to anything that might come in the exam.
Yeah, I have no idea if it's going to come up in the exam. No one shows me that stuff.
I doubt it.
But I doubt it.
Okay.
No. Remember the feeling of I don't have to worry about it. That's what you remember. Okay, sweet. One day I'll get Nick Faulkner, who's, you know, the deputy head of the Maths and Computer Science School, to tell me about it, but haven't succeeded yet. He's very nice, but, you know, he's deputy head of school, so he's very busy. Yeah. Okay, diagonalisation. Let's go. What I'm actually going to do, have a drink. I was going to say as well, thank you for asking the questions, interrupting me and telling me when things don't make sense. It's your revision seminar, so but also it just says to me that you trust me, so thank you. I appreciate it. All right. How do people feel about orthogonal well, no, not even orthogonal, just diagonalisation? Okay. Yeah, I've got people going, not this, sort of. Okay. What is it? I just want to know what someone thinks it is. Yeah.
I watched a video where it said it's to find a similar-ish matrix that helps us do calculations easier.
Okay, so find a similar-ish, whatever that means, matrix that helps us do calculations easier. Cool, that sounds reasonable. Orthogonal set of vectors in a matrix. Cool, 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 cool. They're all there. It's a complicated thing, and that's why it's complicated. People want to talk about it. The first thing I'm going to say before I do anything else is that there are two kinds of diagonalisation. There is ordinary diagonalisation and orthogonal diagonalisation. One of the problems that's happened over the last few weeks, no, it's summer school, week. It's not a few weeks in summer school, it's just a week. Feels like a few weeks, but is that I've had people in the Maths Learning Centre not realising that these were different things. They're very similar. They are both a kind of diagonalisation. And the reason it's called diagonalisation is that any word that begins isation is a process that turns things into what this is. So it's a process that turns a matrix into a diagonal matrix. So that's what diagonalisation is. And so what it is you have a matrix, and then you find a matrix P, and then P inverse AP comes out to a diagonal matrix. That's ordinary diagonalisation. You start with the matrix A, you find the matrix P using the matrix A, and then you do this calculation and it comes out diagonal matrix. Cool. Orthogonal diagonalisation, you have a matrix A, you find the matrix P, and then you do P transpose AP and it comes out to a diagonal matrix. That's the difference. That's the main, there are more differences, but that is the main superficial difference, is that this is P inverse and this is P transpose. Yes?
Ordinary, it's just you can read off the ordinary first thing in the diagram, right? And then you can't do that.
No, you can. So I will get back to that. Yep.
If a matrix is orthogonal, isn't P inverse P transpose?
It is. So let's just add some of those details. So we're going to add some details. So we're going to add the details that are, we're going to find P, and P inverse is the same as P transpose. So this is in fact exactly the same as this. This really is P inverse. It's just that for the matrix P, the P that we find, P inverse happens to be the same as P transpose. So diagonalisation is this. Orthogonal diagonalisation is that you manage to do it in such a way that P transpose is the same as P inverse, which means that you can calculate the inverse of P much easier because it's just the transpose. All right. Right. In both situations, the matrix D, I'm going to use a different colour. In both situations, the matrix D has eigenvalues of A down the diagonal. That makes no difference. It's the same in both. And in both situations, the columns of P are eigenvectors. But over this side, they can't just be any eigenvectors, they have to be orthonormal. And the columns being orthonormal will guarantee that P inverse is equal to P transpose. So you won't have to check that if you make the columns orthonormal. And finally, not all matrices are diagonalizable. Not just any matrix will be able to be some matrices there will not be a matrix P that does this. Almost no matrices are orthogonally diagonalizable. The only matrices that are orthogonally diagonalizable are symmetric matrices. Which is a grand disappointment. It seemed like such a nice thing to be able to do. Only works if the matrix is symmetric. This will work. So A has to have enough linearly independent eigenvectors, where enough means an entire matrix worth. So there are lots of diagonalizable matrices. I mean, if you pick a random matrix, the chances of it being diagonalizable are actually quite high. If you pick a random matrix, really unlikely for it to be symmetric. Yeah. So there you go. And all symmetric matrices, in fact, are orthogonally diagonalizable. That's great. I don't know if this arrangement of it is helpful to you. It helped me just then. It's a really useful thing to do in any situation where there are two similar things, to line them up next to each other and notice specifically how they're similar and how they're different. This is how the entire of science works, or at least biology. But maths is about that too. We only have names for things because we need a word to distinguish between the options. So, yeah. So, whether you're going to diagonalize or orthogonally diagonalize a matrix, you have to find the eigenvectors. That's what you're going to have to do. And you have to find the eigenvalues in order to find the eigenvectors. Not technically true, but if you have found your eigenvectors and eigenvalues correctly, you will not have to do this multiplication. It will automatically work out this way. And as long as you trust your working, you can just trust it. If you have time, you can check it. Okay. Would you like me to diagonalize a matrix? Yes.
So also orthogonal
Yep.
diagonalization. When you're finding P, do you just have to normalize the eigenvectors because they're already orthogonal, or do you have to do the full branch?
Give me a minute. Someone's leaving, I just wanted to say. Right, so your question was what, sorry?
So for orthogonal finding P, which is made up of the eigenvectors of A, to make it an orthonormal basis, you just have to normalize them. Is that already orthogonal, or do you have to do the full Gram-Schmidt thing?
Okay, so the answer is a bit of both. So I'll get to that.
Cool.
But you don't have, so it says here you just have to have enough linearly independent eigenvectors, and this one you need enough orthogonal eigenvectors. You only have to do that within each eigenspace separately. So if you have an eigenspace that is bigger and has two basis vectors, you'll have to do the Gram-Schmidt process inside that little eigenspace, but you won't have to do it across the entire of all the vectors all at once.
So like if it's multiplicity, it's more than one.
Yeah.
Yeah.
But it's not just normalized.
Yeah.
Yeah.
So yes, in a technical sense, for this one, you have to do the Gram-Schmidt process inside each eigenspace. But if the eigenspace has only got one vector in it, that's the same as just dividing by its length.
Yeah.
This one, you don't have to do anything.
Yeah.
Yep.
Does that mean that the vectors in the column P don't have to be orthogonal?
On this side, no.
On the other side?
On this side, yes, they do. But in a symmetric matrix, eigenvectors that go with different eigenvalues are guaranteed to be orthogonal. Right. So, useful facts. Right. Eigenvectors with different eigenvalues are linearly independent. And useful fact number 2, for a symmetric matrix, eigenvectors with different eigenvalues are orthogonal. Also independent, but like eigenvectors with different eigenvalues are linearly independent for any matrix whatsoever. But if you've got a symmetric matrix, eigenvectors with different eigenvalues are independent, but also orthogonal as well. So, and what that means is you only have to think about each eigenspace separately in this process, either way. Okay. It's just going to take a moment for me to think of a matrix that's going to work in any reasonable way. Bear with me. Okay. Crap. Just a second. I hope this works. Oh, crap. Nope. This is my matrix. Top row is 3, 0, minus a half. Second row is 1, 2, minus a half. Third row is 0, 0, 2. Okay. Look at me not using whole numbers. I'm terrified this is going to turn to crap, but there we go. So if I diagonalize this matrix, my goal is to find a matrix P and the matching matrix D. So when they say diagonalize, that's what they mean. So in order to do that, I'm going to have to find the eigenvalues and the eigenvectors. I want to see if someone can guess one of the eigenvectors. Well, the eigenvalues is 2. Why?
Because the balance is 0, 0, 2, and I think there is a rule somewhere about that.
So there is a rule about that. It's not written in your notes, but it is the truth. If you can break your matrix into blocks, and in one of those blocks it's either just a single number or a diagonal matrix, then they will be the eigenvalue and eigenvalues. I was thinking of something else entirely, which is if one of your columns is a multiple of the matching column of the identity, then it's an eigenvector. Yeah. So if I multiply this matrix by 0, 1, 0, it'll tell me what the middle column is, and the middle column is 0, 2, 0, which is 2 times the matrix, the vector I started with, which means that matrix times vector is 2 times vector, and so 2 is an eigenvalue. It happens more often than you think, because your lecturer knows that this is how to make a matrix with a specific eigenvalue, and so it's about the psychology of how lecturers write questions. Oh no. Don't do that. Sorry? The computer just turned off the charger. Before the battery runs out. Document camera is just... The document camera's name is Hugh, by the way. H-U-E. Okay, moving on. But suppose you didn't notice that. So I will say it is totally okay for you to notice one of the eigenvectors and just say this. Like you could say, this is a thing that you could say. You could say note A times 1, 0, 1, 0 is 0, 2, 0, which is 2 times 0, 1, 0. So therefore 0, 1, 0 is an eigenvector with eigenvalue 2. And you're allowed to just say it if you want. And if you can think of enough of those, then you'll just have it without doing the traditional method. It's rare. Can I tell you the other one? 1, 1, 0 is an eigenvector. Because 1, 1, 0 will add the first 2 columns together, and that'll give me 3, 3, 0. Cool, huh? So when you multiply a matrix by a vector, it says this many of the first column and this many of the second column and this many of the third column. So 1, 1, 0 will add these together, which is 3, 3, 0, which is 3 times the original, so it's 3, 3. So 3 is an eigenvalue, and an eigenvector that goes with it is 1, 1, 0. And since the eigenvalues have to add up to the same answer as the trace, the other one has to be 2. Because the trace is 3 plus 2 plus 2, and I've already got a 3 and a 2, so the other one's 2 as well. Yay! Anyway, just wanted to point out that it's actually okay for you to make that sort of reasoning if you notice it. You have to be thinking very clearly, and it's unlikely in a stressful situation, but just wanted to say it. And I will also say, it is very common for exam questions about eigenvectors to give you one of the eigenvectors by telling you this fact. Like A times 0, 1, 0 is 0, 2, 0. Or just telling you that 0, 1, 0 is an eigenvector, and then you go, oh, I'll just multiply it by the matrix and that'll tell me what the eigenvalue is. So that sort of reasoning of either giving you an eigenvector and not telling you its eigenvalue, or telling you that A times vector equals equals some vector which happens to be number times that sort of stuff happens because it can shortcut the working to get to the end. So don't always just go straight to doing your lambdas and crap, because sometimes they give you the information you need. It happened in one of the assignments this semester. They said they didn't tell you what A was, and they said A times this vector is this, A times this vector is this. What's the matrix P that diagonalizes it? And you had to notice that they are eigenvectors. And so just, they've done it to you already. It's not that they can do it again. Yeah, so just don't forget that you're always allowed to go A times vector is number times vector, and then that's an eigenvector. Cool. All right, but I'm just going to find the eigenvalues. And I'm just going to write them as E values if that's okay. Yeah. So I'm going to call it eigenmale. Yeah, so it's a really bad maths dad joke. They're the worst kind of dad joke. So let's find the eigenvalues. So we're going to find the eigenvalues. Of course it is. I've still got half an hour, haven't I? Yeah, that's the power cord's not working. I just have to go get a different power cord. I'll be back, hopefully in time. I'll try not to record my journey. Should be only 2 minutes. Very proud of it. Okay. Made it. All right. So I know that in my head what I'm thinking is we're eventually trying to solve that. And you can rearrange that into this. Lambda I minus AX. You can do it as A minus lambda I, or lambda I minus A, doesn't matter. I'm just used to this one. But some lecturers will do one, some will do the other. The only one I'd say is that if someone asks you for the characteristic polynomial, you have to do this one. Or at least do whichever one you want and just make sure that multiply it by -1 until the biggest power has positive. Yeah. Characteristic polynomial has to have lambda to the n at the front with a plus. So, cool. I'm going to do this. So lambda I would be, and then zeros everywhere else. That's what lambda times I is. And then I have to take the matrix A off of that, which means I have to switch the signs of all of these things. So I took this thing and I put them all as minuses. So that's my lambda I minus A. And I need the determinant of that matrix. So what I'm going to do is I'm going to pick the row or column with the most zeros in it. Doesn't really matter which one. I could pick this row or I could pick this column. Doesn't matter. I choose this row. And so it'll be plus minus plus 0 times a determinant. But I don't care what that is because it's going to be times 0. Minus 0 times a determinant, but I don't care what that is because it's times 0. Plus lambda minus 2 times the determinant of the matrix that's left over. Cool, and that's neatly factorized for me. And so the determinant of this matrix will be lambda minus 3 times lambda minus 2 minus 1 times 0, if just to do the whole thing. And so I get lambda minus 2, lambda minus 3, lambda minus 2. And look, it's all factorized for me neatly to begin with, and that's very pleasant. It doesn't always happen. But what I will say is if you're lucky enough to have a column with mostly zeros, then it will give you a lambda minus whatever out the front, and please do not expand it out. You don't need to expand it out. The whole point of a characteristics equation is to factorize it. In fact, expand out this bit in order to factorize it, but the whole point is to factorize it, so don't expand it out. No one cares. It's totally okay to present the characteristic polynomial as the factorized version. So, yeah, unless they specifically ask what one of the coefficients was. Annoying of them. Okay, so I've got the eigenvalue 2 and the eigenvalue 3, and the eigenvalue 2 appears twice because it's got 2 factors. So it's got multiplicity 2. So my eigenvalues are this. And just list it twice if it's there twice, just so that you know the multiplicity. But if you like, you can say multiplicity 2. And the reason you need multiplicity is so that the theorem that says when you multiply the eigenvalues you get the determinant, and when you add the eigenvalues you get the same as the trace, it still works. It doesn't work if you don't include them more times than things. And mathematicians are nothing if not people who like to have a nice, neat rules that cover everything. So, yeah. Okay. So now we've found the eigenvalues, we have to find the eigenvectors that go with them. You may notice that I'm writing in my working the title find the eigenvalues and the title find the eigenvectors. That's a really good thing to do, so that the person reading it knows what you're doing. And so that you can find the beginning of this piece of working, so that when you're looking back through your working, you don't go too far. So find the eigenvectors, we need lambda equals 2, which means we have to go back to this matrix lambda I minus A and solve that matrix times x equals 0. So what we're actually doing is we're going back to here. We're going lambda equals 2 in there. So 2 minus 3 is -1. 2 minus 2 is 0. because we're technically solving this times x equals 0. You don't have to put the 0, 0, 0 in there, but it reminds me that there is an answer that I'm looking for. So those two rows are the same, so they're going to, if I do the right row operation, one of them will disappear, and I can get this. And that's in reduced row echelon form. And so I get one pivot and two free variables. Yep. It should. Good move. I just want to say there's nothing stopping you putting the pivot over here if you prefer not to have fractions, but whatever. So now, this is a really important point. This column of zeros does not mean that the second variable is 0. It can be anything. These equations, you know, if this is like x1 and x2 and x3, 1x1 minus a half of x3 is 0, and the equations do not mention x2, so x2 can be whatever you want because it doesn't come into these equations. It's free because it's not even there. And it's also free because it doesn't have a pivot in that column, because there's nothing in that column. So there's a pivot here, which means that x2 and x3 are free. Actually, it's probably better to go S and T, or I'm going to get them backwards. And then x1 is, well, there's 0 x2s, and minus a half of x3 is 0, so if I move that over the other side, I'll get plus a half of x3, but x3 is really t. So I'm taking this equation, and that's what's producing this. And so I get x1 and x2 and x3 is half of t, s, and t. So that's s lots of 0, 1, 0, and t lots of a half 0, 1. Well, that is badly written. So I get my two eigenvectors, two linearly independent eigenvectors to go with this one eigenvalue that appears twice in the list. So because there's 2 to go with the multiplicity 2, it's going to end up being diagonalizable. Yep.
If the second column x2 is x3 and 1,
Yep.
does that mean x2 equals 0 then?
Correct. So if, I'm just going to repeat that. If there had been a 1 here, then x2 would be 0, which means we would have only ended up with one vector. And so it would be multiplicity 2, but there was only one vector to go with it, and it wouldn't be diagonalizable. So for lambda equals 3, if I go back to my original lambda I minus a, I get 0, 0, a half, minus 1, 1, half, 0, 0, 1. And then I can add this column, well, subtract it from the other ones to get zeros in those spots. And so if I do the reduced row echelon form, I will get, no. If you trust yourself, you don't have to explain the steps for that bit, I think. Unless I explicitly tell you to. But as you said, that's a Maths 1A thing. And they don't care about that anymore. Other than it preventing you from getting the right answer in Maths 1B if you do it wrong. So I can see that this will clear those. And so I'm definitely going to have a 0, 0, 1. Clearing that, we'll put a row of zeros in that one there. And then if I minus this one, it'll put the 1 in a convenient spot. And I was able to do that reduced row echelon form without having to enter it into a calculator because I could see what was going to happen. I'm going to, well, I'll clear those, that'll put zeros, and then I'll minus, oh no, that'll be a 0 here. Because I cleared that, didn't I? Should have crossed them out. Yeah, okay. So I get minus 1, 1, 0. And so I've got two pivots now. And so I'm going to let x2 be equal to t, and so x1 will also be t, and x3 will be 0 because that's what this row says. So it's no x1s and no x2s, and 1x3 equals 0. Right, and so I've got that x1, x2, x3 is t0, which is t lots of 1, 1, 0. And so what I've got is that the eigenvectors for lambda equals 2, I've got a basis of 0, 1, 0 and a half 0, 1. And for lambda equals 3, I've got a basis of 1, 1, 0 for the eigenspaces. I'll say eigenspaces this time. Because I've mentioned the word basis, that means it belongs to a space, so I'm talking about eigenspaces. Yep. Yeah. Yeah, so if I didn't have enough, so I've got 3 vectors total here. 3 vectors total, and it was a 3 by 3 matrix, so it's diagonalizable. But if I didn't get 3 vectors total, it wouldn't be diagonalizable. Yep.
Can we ever get 4 vectors from this matrix?
You can never get more vectors than there are the columns. You could, I mean, technically if I add these two together, there'll be a new eigenvector, but that wouldn't be a basis for this eigenspace because this eigenspace is dimension 2 because they're not these 2. So, yeah. Yeah. So, yeah, this is the basis for this eigenspace. Technically, any combination of these is also part of that eigenspace because every vector that I could possibly multiply by the matrix and get 2 of the original vector is made by doing a combination of these 2. But I only need these 2 to make all the rest of them. So that's why it's really important to talk about a basis. How you guys doing? You right? Cool. All right. So that means if I'm doing ordinary diagonalization, which I have to because it's not symmetric, my original matrix isn't a symmetric matrix because that doesn't match that. I don't have to do anything to these vectors. I don't have to do anything to these vectors because you don't have to do ordinary diagonalization. So P can be made out of these vectors, and it doesn't matter what order you put them in, as long as the matrix D has the eigenvalues in the same order. So this eigenvector went with 2, so I put a 2 here. This eigenvector also went with 2, so I put a 2 here. This eigenvector went with 3, so I put a 3 here. But I could have just as easily switched these 2 and just switched these 2 and it would still be correct. Then P inverse AP will be equal to D. So if someone says that you have to diagonalize something, you must mention this fact somewhere. You don't have to do the calculation necessarily, but you have to mention that it is true. Yeah. Cool. Now, there are many answers to this. As I said, I could have switched these 2 and switched these 2 and it would still have been true and correct. So there's more than one way to diagonalize a matrix. But no matter which way you do it, these will be eigenvectors and these will be their matching eigenvalues. Yep. I'm going to do that too. Yeah. But yes. You right? Cool. All right. You could even have multiplied this one by 2 and it would have been fine. Because it's still an eigenvector that's different to that one. Right. So I'm just going to just show something. This matrix, pretty sure, is not diagonalizable. So this matrix, all of its eigenvalues are 1. because it's an upper triangular matrix and there's a shortcut. If half your matrix is zeros, then there's a shortcut that the eigenvalues live on the diagonal. So that's a theorem that you're allowed to use. So it's upper triangular. Well, it's just triangular. Even if I make this a 4, it won't matter. 1 and 1 and 4. And so if I find the eigenvector for lambda equals 1, damn it. I'm just going to write down what lambda I minus a is so that I can, because I'll feel bad about it. So lambda minus 1. Which is why the eigenvalues come out to 114, because when you find the determinant of this, you just get this times this times this, because of all the zeros. Okay, so so 1, 0, 4. All right, that's what I'm doing. You can see my brain works in a certain way. I have things that I fill in, and that's why I have to write this, or I can't write this. And so when I do the reduced row echelon form, I've got pivots here, and I get only one free variable. And so, you know, I'll get x1 equals s, and so I'll get x2 is 0 and x3 is 0, so I get s0, 0. And so the eigenspace for 1 is the span of 1, 0, 0. But it had multiplicity too, and I only got one eigenvector, so it's not diagonalizable. Yeah. The number of vectors in your basis for your eigenspace has to be the same as the multiplicity for every eigenvalue, and then it'll be diagonalizable. So what that means is if a matrix has got a list of all different eigenvector values and none of them are repeated, it's guaranteed to be diagonalizable because each eigenspace is automatically going to have one vector to go with it. You can only get non-diagonalizable matrices if one of the eigenvalues appears more than once. And then, if you get enough eigenvectors, it's still diagonalizable. As I said, it's going to be quite difficult to have a not diagonalizable matrix that's just random, because a random matrix is much more likely to have all different eigenvalues. So, yeah. So if someone asks you, is this matrix diagonalizable? You have to find the eigenspaces, or at least, like, if here I had gotten 1, 3, and 4, then I would have said, yes, it is. If all the eigenvalues are different, all the eigenspaces have the correct dimension for the multiplicity, and therefore it's diagonalizable. But if one of them happens twice, then you only need to find the eigenspace that goes with the repeated eigenvalue to see if it's got enough vectors in it. Yeah, to tell if you just to decide whether it's diagonalizable or not. So if all they ask you is this diagonalizable, then you can stop early if you've done that. So I don't have to worry about the 4 for this one. So I'm just going to is it diagonalizable? But is a classic, at least assignment question, say, is it diagonalizable? And if it is, diagonalize it, which is usually a hint that it is. But you never know. Yep.
What if it was 1, 1, 1?
So if it was 1, 1, 1, if there was a 1 here, that's still okay. Yeah. Actually, it might cause something different if there was a 1 here, then there would have been a 1 here. No, that would have been cancelled out by this, so that it would still have the same issue. But sometimes if you change enough of them, it'll happen. I don't quite understand all the details of how to make one up that does that, but usually if you make a little part that looks like this, then it will do the trick. It's, yep.
Wait, so the bottom if then zeros, then eigenvalues would just be the diagonal.
Correct. So if these are all zeros and the eigenvalues are there, works just as well if the top is zeros as well. It doesn't matter which half is zeros, or both, right? Yeah. So I'm sure it's a theorem in the notes. Eigenvalues aren't in 1A. Yeah, but you are correct. If all of these are zero, then the eigenvalues are there. Or if all of these are zero, then the eigenvalues are there. So, yeah, if you don't have enough zeros on both halves, then you're just going to have to do it properly. Yeah. Sadness. Okay. So, for orthogonal diagonalisation, 5 minutes, but I can go over. For orthogonal diagonalisation, you need your matrix to be symmetric to begin with. So this would be a classic true or false question, right? Is this matrix orthogonally diagonalisable? And you go, not symmetric, no. Fabulous exam question that would look like it has lots of work, but it's not. So I just that's the question I would ask if I was setting an exam. I like yes or no questions. You've got to look very closely. Is this a yes or no question? And so does that mean it's easy to answer? Yeah. I wouldn't give true or false questions. I'd just ask questions in the middle of nowhere that were yes or no questions. I'm going to call it B today because I feel... It's going to turn to shit, but it's okay. This is a perfectly good symmetric matrix. Symmetric matrix, its transpose is the same as the original, which means that the first column is the same as the first row, and the second column is the same as the second row, and the third column is the same as the third row. It's a symmetric matrix. So I would just check that, because if they had made a typo and they'd said orthogonally diagonalised B, and you go, it's not a symmetric matrix, it's not possible. Done. That happened in one of my third year assignments. It wasn't for this, but it was something else. The lecturer asked us to do something and it wasn't possible. And then she changed the assignment question to say, what does this number here have to be in order for it to be possible? So, yeah. Okay, so to orthogonally diagonalise this matrix, you would have to find its eigenvalues and its eigenvectors. I probably made it way too hard for myself. But, you know, let's go. So I'm going to have my lambdas, minus 0, minus 1, minus 3, minus 1, minus 6, minus 2, minus 3, minus 2. Ugh. Should have put more zeros in there. The nice thing about symmetric matrices is they're guaranteed to have real eigenvalues. It's very annoying when you have complex eigenvalues, like all numbers are complex numbers. Very annoying when you have unreal eigenvalues. But a symmetric matrix is guaranteed to have all of its eigenvalues being real if you put real numbers in. Okay. Sorry? It's lambda minus 0. I shouldn't have done this. I'm going to change the original matrix. Let's change it to this. Okay. So just pointing out, this is not a triangular matrix. half of the values are 0, but it's the wrong half. It's only the half. If you do the downwards diagonal, if this half is 0 or this half is 0, then you can do the thing, but this is the upwards diagonal, it's the wrong half. It probably still will have those eigenvalues actually, but I could be wrong. Okay. So it's not nearly as nice as the other ones I've got. I don't have a full row of zeros except for lambda. I need to pick which row or column I'm going to use. Thoughts? Obviously the top one of these two, but it could be one of these two.
Could you do it across the columns?
Sorry?
Could you do it across the columns?
Yeah, like down here.
Yeah, because I always do it and I get a different answer to what I do when I do it across the columns.
All right. Actually, let me go down the middle column. No, I'll go down this one. So the determinant of lambda I minus a. So it always goes plus in this top left corner. So plus lambda times something. And that something is lambda minus 6 minus 2 lambda. Minus 0, and I don't really care what I multiply that by because it's times 0, plus minus 3. All right. I don't like it. So I've got lambda minus 6 times lambda minus 2 times minus 2 is 4. And I've got 0 times minus 2 minus 3 times lambda minus 6. All right, so I don't like it. You say just make it into a cubic as if that's like an easy thing to deal with after it's a cubic. Lambda squared minus 6 lambda minus 4. So I've got a minus 3 and a minus minus 3, which is 9, which is a minus 9, like minus minus minus. All right, I don't have a choice. If I was really lucky, I would have been able to factorize something out at this point. But this lambda minus 6 is trapped with this minus 4. And right. See how I did that? 9 times 6 is 54, because like 10 times 6 is 60, and it's 6 down from there. Yeah. I only know about 70% of my times tables. I know my squares. Good at squares. Wow, yeah, interesting.
And you just put it in the calculator.
Yes, that's what calculators are for.
And then it gives you various bad numbers.
Bad numbers. So lambda equals bad numbers. All right, damn it. Yeah. I could have, but it would only help if it was this thing. All right, just a second. I really want one that actually goes somewhere, so I'm just going to make a matrix that will work. Maybe I should do it 2 by 2. No, 3 by 3. Just a second. Just a moment. Ignore the man behind the curtain. Perfectly good symmetric matrix. Yes. And its eigenvalues are 3 and 3 and -1. All right. Sorry, I know it's gone, but I just needed to change those to B's because that's what they were. Yep.
So in that matrix C,
Yep.
if you were to take like 2 times row 2 onto row 3, that would give you a triangle. Can you still do that?
No, because that changes what the matrix is. Yep.
Your bottom right lambda could be lambda minus 1.
It so should be. Thank you. Thank you, small error fairy. I've said this in multiple revision seminars, but too bad. In the film Barbie Princess Charm School, they all get a fairy helper. I've always wanted one for maths exams. Could look over my shoulder and do what you did. Yeah. So I can see already if I go down this top row or along this down this left column or along this top row, I'll get a lambda minus 3. Just to completeness sake, to say that I really did it. And then I don't have to factorise that out. And this will be lambda minus 1 squared minus 2 times minus 2, which is the same as 2 squared. Oh, and look at that, it's a difference of 2 squares. So cool. So this will be lambda minus 1 minus 2 and lambda minus 1 plus 2. And so I get lambda minus 3, lambda minus 3, lambda plus 1. So the eigenvalues are lambda equals 3 and minus 1. Told ya. This is one of my favourite moves. Doesn't happen that often. Just love it when it does. You can actually factorise all quadratics by using that move. It's what completing the square is, if you do it right. So, one of those. Yeah. So
what you did was I know one way that just do whatever the constant is, let's say you have plus 6. Minus 1 times whatever constant. But that would just give a specific value.
yeah.
Yeah.
So if you do have a random cubic like this one, if you're very, very lucky, one of the roots will be a whole number, and if there is a whole number that's a root, it will divide into this. And so you can find the numbers that divide into this and sub them in and see if any of them come out to 0, and then you know it's a factor, and you can use long division to divide it out, and then factorise the quadratic that's left over. But in exams, your lecturers will try very hard to give you matrices that don't require you to do such a thing. They'll either give you 2 by 2 matrices or 3 by 3 matrices with enough zeros that it's partly factorised for you, because they don't want you to waste time factorising things. And they also just love it when it's partially factorised for you, because it just appeals to their sense of mathematical coolness. So now I would have to find the eigenvectors. I'm guaranteed to get enough eigenvectors for each eigenvalue, because symmetric matrices are guaranteed to be diagonalisable. So I'm not going to have that problem of only getting one eigenvector from my lambda equals 3. So what that means is if it's symmetric and you only don't get enough eigenvectors for your eigenvalue that's got multiplicity 2, then you've done it wrong. So I just wanted to point that out. That's a nice thing, that if it's a symmetric matrix, you're never going to not have enough. So lambda equals 3, I go back to here, and I put lambda equals 3 into this. 0, 0, 0, 0, 2, minus 2, 0, minus 2, 2. That column of zeros again, that's going to cause my that's going to cause my free variable. So I remove my row of zeros to the bottom. This row is minus that row, so it'll cancel the other one out. Divided this one by 2 and put it at the top. So that was like 7 row operations. But if there's enough zeros in it, you can usually see it. Okay, so I've got one pivot there, and the other 2 are free. So x1 is S, and x3 is T, and x2 will be also T, and so I'll get S times 1, 0, 0, plus T times 0, 1, 1. Now you can see how I made my matrix. I made the second 2 columns add up to 3. And so they're my eigenspace. And when lambda equals, okay, stop. Just going to leave some space here. It's probably not enough space, but it doesn't matter. I'm going to do my lambda equals minus 1. So when I go back to my matrix, minus 1 minus 3 is minus 4. Is it minus 1? Okay. Minus 1 minus 2 is minus 2. Divide this one by minus 4, I'll get 1, 0, 0. This will be 0, 1, 1, and they're the same row, so they'll cancel each other out. And so I've got a pivot here and a pivot here, one free variable, that's good, I should only have one free variable. And so I get x1 is 0, that's what this row says. X2 is going to be, well, x3 is going to be my free variable. And x2 is going to be minus t. And so therefore my eigenspace basis for eigenspace for -1 is, nope. Okay, so here's the thing. Yeah, so if I was just ordinary diagonalizing this, I could just use these matrices as these vectors as they are. So just look closely, even if it's a symmetric matrix, you don't have to orthogonally diagonalize it, you can just ordinary diagonalize it. So if I was just ordinary diagonalize, I just use the vectors as they are. But if I want to orthogonally diagonalize, then I have to, I should really say, yeah. Then I have to make my vectors an orthonormal basis. But I only have to do it one eigenspace at a time. So these two I have to turn into an orthonormal basis just inside these two. And so I'm going to need to do the Gram-Schmidt process on this basis. So I've got my first vector. The length of that is already 1, and so we're good. We don't have to do anything. So I've done the normalize for the first step. Second step, I'm going to have to project, subtract, and normalize. Oh, look, it's already orthogonal to that one. That's cool. Oh, yay. I don't have to do anything. But anyway, to project, I would dot this with the other vector and times it by the other vector. And that'll give me 0 times 1, 0, 0, which is just 0, 0, 0, and subtract. Damn it. The vector I had minus the projection and then normalize. And so I'd get 1 on root 2 because that's how long this vector is. And so my orthonormal basis is 1, 0, 0 and 1 on root 2, 0, 1, 1. And this vector's only got one vector, so the Gram-Schmidt process is just normalizing it. And so therefore, my matrix P that's this vector here, this one just here, and the other one is this. And the matrix D will have the matching eigenvalues in their matching spots. So this one went with 3, this one also went with 3, and this one went with -1. Ta-da! So if I was unlucky, these wouldn't have been orthogonal, but they are. So technically I didn't have to do that whole process there of the Gram-Schmidt process. I could have just noted that the vectors were orthogonal and just divided them by their lengths. But I just wanted to show you the whole thing. Okay. Any last comments or questions? Yes?
I don't know if you have to answer this, but for the students, the only problem I have.
Well, okay. You can ask that at the Maths Learning Centre. I'm not going to do it on the video because I have to go eat before we open the Maths Learning Centre. Yeah. Yep. I'm going to scan them and put them on the website. So you can't have them until I've scanned them. Sure. First in, best dressed. But everyone else, you will get a copy of them. All right, I'm going to stop there. Sorry?